Welcome back to our course, Fundamentals of Operating Systems, based on the textbook Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter B. Galvin, published by Wiley Publishing. We have just completed talking about several process synchronization tools, test and set, mutex locks, and the semaphore. Now we're going to talk about some of the issues that must be addressed to make all this work. So let's continue. Remember that earlier we discussed the three criteria that solutions to the critical section problem must satisfy. If I recall, I actually read the slide to you in detail. Indefinite waiting violates two of these: the progress and the bounded waiting criteria. Liveness refers to a set of properties that a system must satisfy to ensure that the processes make progress during their execution life cycle. A process waiting indefinitely under the circumstances I just described is an example of a liveness failure. There are many different forms of liveness failure. However, all are generally characterized by poor performance and poor responsiveness. A very simple example of a liveness failure is an infinite loop. A busy wait loop presents the possibility of a liveness failure, especially if a process may loop in an arbitrarily long period of time. Efforts at providing mutual exclusion using tools such as mutex loops and semaphores can often lead to such failures in concurrent programming. Let's take a look at two situations that can lead to liveness failure. The implementation of a semaphore with a waiting queue may result in a situation where two or more processes are waiting indefinitely for an event that can be caused only by one of the waiting processes. The event in question is the execution of a signal operation. When such a state is reached, these processes are said to be deadlocked. Take a look at these two processes, P0 and P1, each accessing two semaphores, S and Q, set to the value of 1. Suppose that process 0 executes a wait on semaphore S, and then process 1 executes a wait on semaphore Q. When process 0 executes a wait Q, it must wait until process 1 executes a signal Q. Also, when process 1 executes its wait S, it must wait until process 0 executes a signal S. What a mess! Since these signal operations cannot be executed, process 0 and process 1 are deadlocked. We say that a set of processes is in a deadlocked state when every process in the set is waiting for an event that can be caused only by another process in the set. The events with which we are concerned here are the acquisition and release of resources such as mutex locks and semaphores. Other types of events may also result in deadlocks. A scheduling challenge arises when a higher priority process needs to read or modify kernel data that are currently being accessed by a lower priority process or a chain of lower priority processes. Since kernel data are typically protected with a lock, the higher priority process will have to wait for a lower priority one to finish with the resource. The situation becomes more complicated if the lower priority process is preempted in favor of another process with a higher priority. As an example, assume we have three processes, L, M, and H, whose priorities follow the order low, medium, and high. Assume that process H requires a semaphore which is currently being accessed by process L. Ordinarily, process H would wait for L to finish using a semaphore. However, now suppose that process M becomes runnable and preempts process L. Indirectly, a process with a lower priority, process M, has affected how long process H must wait for L to relinquish resource S. If this happens repeatedly, process H could be seriously delayed, creating a situation referred to as starvation. Process H would starve because of the actions of the other lower priority processes. This liveness problem is known as priority inversion, and it can only occur in systems with more than two priorities. Typically, priority inversion is avoided by implementing a priority inheritance protocol. According to this protocol, all processes that are accessing resources needed by a higher priority process inherit the higher priority until they are finished with the resources in question. When they are finished, their priorities revert to their original values. In the example we just saw, a priority inheritance protocol would allow process L to temporarily inherit the priority of process H, preventing process M from preempting its execution. When process L had finished using resource S, it would relinquish its priority from process H and assume its original priority. Because resource S would now be available, process H, not process M, would run next. We have talked about several different synchronization tools that can be used to solve the critical section problem. Given correct implementation and usage, these tools can be used effectively to ensure mutual exclusion as well as address liveness issues. With the growth of concurrent programs that leverage the power of modern multi-core computer systems, increasing attention is being paid to the performance of the synchronization tools. In summary, a race condition occurs when processes have concurrent access to shared data and the final result depends on the particular order in which concurrent accesses occur. Race conditions can result in corrupted values of shared data. A critical section is a section of code where shared data may be manipulated and a possible race condition occurs. The critical section problem is to design a protocol whereby processes can synchronize their activity to cooperatively share data. A solution to the critical section problem must satisfy the following three requirements: mutual exclusion, progress, and bounded waiting. Mutual exclusion ensures that only one process at a time is active in its critical section. Progress ensures that programs will cooperatively determine what process will next enter its critical section. Bounded waiting limits how much time a program will wait before it can enter its critical section. A mutex lock provides mutual exclusion by requiring that a process acquire a lock before entering a critical section and release that lock on exiting the critical section. Semaphores, like mutex locks, can be used to provide mutual exclusion. However, whereas a mutex lock is a binary value that indicates if the lock is available or not, a semaphore has an integer value and can therefore be used to solve a variety of synchronization problems. Solutions to the critical section problem may suffer from liveness problems, including deadlock and starvation. So that concludes Unit 6 in our discussion of process synchronization. Let's take a break, and when you're ready, let's take a break so that you can review this unit, and when you're ready, come on back and we will begin Unit 7.